it says use Green's theorem to find the work done by the force field F, which has components x squared y and y times the quantity x plus y, in moving the particle from 0, 1 along the y-axis to the origin, and then along the x-axis 1, 0, and then along the straight line segment back to 0, 1. Let's graph this thing so we can see the region that is enclosed by these line segments. So, okay, so here's x, here's y. So we're going to need to go 0 to 1. Okay. So where are we going? We're going from 0, 1. That would be this guy, right? Along the y-axis to the origin, that would be to here, right? So like that. And then to 1, 0, which would be here. And then along the straight line segment back to 0, 1, so that would be here. So the first thing you want to observe is it oriented counterclockwise? So you're good to go there for Green's theorem, right? So Green's theorem says that the line integral with respect to the vector field is going to be equal to a certain double integral over this region, which you could call R right here, enclosed by C, where C is actually the union of, if the hypotenuse is C1, the vertical line C2, the horizontal line C3, C would be the union C1, union C2, union C3. The Green's theorem says that there's a certain double integral that will be equal to the value of the line integral over C f dot dr. And that's the double integral over what I called R over here of, okay, remember what it is? dq dx minus dp dy. What's q and p? P and q? Well, not necessarily. The components of the vector field, right? So this guy, x squared y, would be p, and y times quantity x plus y would be q, right? We don't know if the vector field's conservative, so we can't call p f sub x. We can't call q f sub y. Green's theorem works if it can work if the vector field is not conservative. So what does the formula on the right-hand side tell us to do? Let the formula be your guide. Your life will be a lot easier if you just memorize the formulas and then let the formulas tell you what to do. There's less thinking involved if you do it that way. Okay, wait, don't get the wrong idea. It's important to think. Don't not think. But the idea is to make it routine. So there's been studies done. If you guys try to learn something new, you're a lot younger than me, you'll be able to do it a lot faster, right? But I've been doing this so many years that I don't even think it's hard to do these questions as used because it's routine, right? It's like if I actually knew how to play guitar, and I try, but I'm not very good. But if I were good at playing guitar, is the guitarist thinking, oh, I have to hit this string and then this string and then this? No, he or she is just doing it, right? It's like that. The brain, after you get enough practice in, isn't working as hard. It becomes routine, and that's where you want to be. That's where you want to. So, make some flashcards, memorize the relevant formulas, look at them before you go to bed at night, and then let the formulas be your guide. dq dx, what's that? Oh, maybe we should multiply out the q. So q, if you multiply it out, what would that be? xy plus y squared. Yeah. So distributing out that y right there. So what's dq, partial of q with respect to x? So just y. Would everybody buy that? Okay. And then what's the partial of p with respect to y? So just x squared. So then your integral becomes this guy minus this guy. Well, for an integrand. And then I'm going to set it up with the usual order of integration. So dy dx. And the good thing about this is you're getting a great review now of the last chapter, right? Double integrals. So if I go with a dy dx order of differentials, that corresponds to a representative rectangle that's what? Vertical or horizontal? Vertical. So that means what? That means if I want to get the top of this rectangle, which gives me my inner limit of integration here, I need to find what? I need to find the equation of that line, right? All right, well, what's its slope? So I'll use this equation. Y minus y1 equals m times x minus x1. That's the point slope form of the line. M looks like it's -1, right? So m is -1, and a point, a point on the line is, you could use either 1, 0, 0, 1. Let's use 1, 0 for my x1, y1, right? So that means the reason I picked 1, 0 is because y is 0, so y1 is 0. So I just get y on the left side, just filling this in, equals -1 times x minus 1, which is what? Negative x plus 1? Does everybody believe that? Okay, yeah? Ryan, you looked like you weren't convinced. Okay, so then the top of this rectangle is given by negative x plus 1. That's your upper inner limit of integration, or 1 minus x would be a nice way to write it too. And then what's the bottom of the rectangle given by? 0. And then what does x run from for the outer limits? 0 to 1. All right, let's integrate. Close it out. Integrate with respect to y first. What do you get? Well, y times x, or x times y, right? And then minus what? Minus x squared y? No, wait, we integrated with respect to y, so let's check that. So how about y squared over 2? There we go. That looks better. And then x squared minus x squared y? Now we're in agreement. Okay, and then 0 to, I'm going to change it to 1 minus x instead of negative x plus 1. I like that better. Dx. Everybody comfortable with that? Yes. So it's y equals 0 that we're plugging in to y equals 1 minus x. So plug in for y, don't plug in for x, right? Okay, so we get what? Integral 0 to 1 of 1 minus x squared over 2, or 1/2 times that, either way. 1 minus x squared over 2 minus what? Don't plug in for x squared. So just plug in 1 minus x. And then that whole thing, that's just plugging in the upper limit, right? So then plug in 0, what happens? You get a nice 0. So that's a good thing. It's a good thing. Who used to say that? It's a good thing. Martha Stewart or somebody used to say that. Don't ask me how I know that. I never watched Martha Stewart. Simplify. Okay, what do we get? Integral 0 to 1, 1/2 times, let's multiply it out. So let's see, 1 minus 2x plus x squared, right? Okay, distribute the minus x squared. What does that give you? All right, it's not quite as ugly as it looked. Is it 1/2 times that whole thing? No, just 1/2 times that. I did close the parentheses, just making sure. And then I'll close some brackets here, right? Then dx, that looks better. Everybody believe that? All right, then let's distribute the 1/2. So 1/2 minus x plus 1/2 x squared. Yeah? Minus x squared plus x cubed, combine like terms. I will put the x cubed in front. Took care of that guy. We've got what? An x squared, a 1/2 x squared term minus x squared. What does that give us? Minus 1/2 x squared. So took care of these two guys, and then we have a minus x and a plus 1/2. Integrate, what do we get? So x to the 4 over 4. Yeah, I don't know why, but I wrote it as 1/6 here and and then divided by 4 here. I don't know. I should be more consistent. And then x squared over 2, and then 1/2 x. And then evaluated from 0 to 1. So it breaks down to just 1/4 minus 1/6 minus 1/2 plus 1/2. That's not as bad as it looks, is it? Because that's gone. And then what's this? See, 12 is the common denominator. So that's 3/12 minus 2/12, which is 1/12. By the way, so what does that represent?
1/2.
What does that represent?
The work done.
So it says use Green's theorem to find the work done. Okay. So I didn't really give you units, but what would the units of work be? Either foot-pounds or, more likely in your physics classes, joules in physics class, right? Yeah. But I didn't specify units, but I just wanted to review that with you. I'm letting you out almost a full minute early.
Oh boy.